everybody. In this class, I am going to show you the process of getting the reduction formula for the integral of 10 to the power of n x dx, this kind of integral. The technique that I am going to demonstrate for this kind of function 10 to the power of x, 10 to the power of n x dx would be similar to the technique for the reduction formula of cot to the power of n x dx. So I will go through this 10 to the power of n dx, this kind of reduction formula, and the same type of reduction formula for cot to the power of n dx that I shall leave for you as a homework. Okay, so look at this technique a bit carefully. Over here, the integral is 10 to the power of n dx. We cannot directly integrate this kind of function. What we are doing over here is that we are keeping tan square x separate. Okay, we are keeping tan square x separate, so that one more factor would be there, 10 to the power of n minus 1 x. N minus 2 x, 10 to the power of n minus 2 x. And this tan square x, this expression, this term tan square x, can be written as sec square x minus 1 dx. And let me show you over here. The direction is already written over here. Yes, this one. So this tan square x, it is now written in this fashion. Tan square x is now written in this fashion, sec square x minus 1. Now if we decompose this total expression, in that case this total expression can be now written as the difference of two integrals. The first integral is 10 to the power of n minus 2 x dx into sec square x dx, and second one is 10 to the power of n minus 2 x dx, this kind of integral. And you see this second integral, in place of the given integral n, in place of this index n, we have n minus 2. Therefore, if this expression or this integral is considered as in, in that case this integral can be considered as in minus 2. So this is a direct and directly we can write it this integral is equal to in minus 2. Now this one, the first integral over here, this sec square x dx. If you write over here, say, let me show you. If you write tan of x is equal to, suppose, z. In that case, we know that dz can be written as sec square x dx. And in that case, this total integral can be written in this fashion. This total integral can be written as, you see, this one, sec square x dx, this one would be equal to our dz. So I can write this expression as equal to dz, d of z, and this tends to the power of n minus 2x, as because tan x is equal to z. Therefore, you can write this expression as z to the power of n minus 2 dz. Okay, and the integral of this expression would be is equal to z to the power of n minus 1 divided by n minus 1. Got it? This kind of expression would appear, and with of course one arbitrary constant, but for the time being let me don't consider this arbitrary constant, and this expression should be written in this way, that this should be is equal this expression this expression should be written in this way, that is actually 10 to the power of n minus 2x divided by n minus 1. Got it? So this expression has been written over here. You see 1 by n minus 1, 10 to the power of n minus 1x. And one more arbitrary constant should come over here, but this arbitrary constant will get adjusted with this integral. You can include the arbitrary constant within this integral, and in that case we don't need to separately write this arbitrary constant. We can say that the arbitrary constant is included in this integral I n minus 2. Got it? And therefore this would be the integral formula. This in is equal to 1 by n minus 1 10 to the power of n minus 1 x minus I n minus 2. This would be the integral formula. This would be the reduction formula, not integral formula. This would be the reduction formula for the given integral 10 to the power of n x dx. Okay, and sometimes this was an indefinite integral. Sometimes the lower and upper limits are given. Maybe that lower limit is equal to 0 and upper limit is equal to pi by 2. In that case, what you need to do in this first term, you just put the upper and lower limit and compute them. So if you put upper limit x is equal to pi by 4, then 10 of pi by 4 is equal to 1, and 10 to the power of n minus 1 x at the point pi by 4, that should also be is equal to 1. And if you put x is equal to the lower limit 0, this lower limit, in that case 10 of 0, that is actually 0. So ultimately the value of this total expression would be simply is equal to 1 by n minus 1. Got it? So the reduction formula should be is equal to in is equal to 1 by n minus 2 minus I n minus 2. So this kind of questions generally come in exam. You don't need to remember the reduction formula. Generally in exam directly they say I deduce a reduction formula, or they just directly say that prove that in is equal to 1 by n minus 1 minus in minus 2. Okay, and in this kind of questions you will get about 4 to 5 marks. So these are quite easy kind of questions. And I'm leaving the corresponding reduction formula for cot to the power of n x dx. Okay, cot to the power of n x dx. So over here, in this book, the reduction formula for sec to the power of n x dx has been given, and I am going to discuss the reduction formula for cosec to the power of n x dx. So I am leaving this reduction formula for you. Hopefully, this would be clear after the discussion of this kind of reduction formula, cosec to the power of n x dx. Both of these two reduction formula are very similar. So let me discuss the reduction formula for cosec to the power of n x dx. Okay. Now this cosec to the power of n, this cosec to the power of nx, we are considering cosec square x as a separate factor, and the remaining part, that is cosec to the power of n minus 2, can be considered as the another factor. And over here, this cosec to the power of nx dx, this is easy to integrate. That's why we are taking this expression, this function cosec square x. This cosec square x is easy to integrate. Therefore, we are taking this function as the second function, and this function has been taken as the first function, and therefore we now apply the integration by parts. All right. Now, after applying the integration by parts, this would be the first function. So this is the first term. That is, first function is taken to be fixed. Then this is the integral of second function. When cosec square x is integrated with respect to x, we get minus cot of x. Then minus the derivative of first function. this is the first function. So its derivative should contain n minus 2 multiplied by cosec to the power of n minus 3 x, and then this cosec x, cosec of x, that has to be differentiated by chain rule, and that derivative would give us minus cosec x into cot of x, minus cosec x into cot of x. So this much would be actually the derivative of first function. All right, and then this is the second function, cosec square x. So cosec square x, when it is integrated, we will get minus cot of x. So this is the derivative of first function multiplied by integral of second function dx. So this would ultimately give us the entire expression or the integration by parts. Now over here, what we observe is that cosec function is there, and cosec to the power of n minus 1 function is there. So if we multiply these two, we will get cosec to the power of n minus 2x. Again, cot of x is there and one more cot of x is multiplied. Therefore, cot square x would appear, and this minus sign and this minus sign, they would, whenever multiplied, they would produce a positive sign, and along with that one more minus sign is there. So this term would have negative sign. The second term would have negative sign. This n minus 2 is considered, is taken outside the integral, and therefore we will have cosec to the power of n minus 2x multiplied by cot square x dx. And we are not changing the first term. Got it? We are not changing the first term at all. We are not changing this first term at all. Now, this cot square x can be considered as cosec square x minus 1, a standard formula. Cot square x is equal to cosec square x minus 1. And then this cosec square x, whenever it is multiplied by cosec to the power of n minus 2 x, they will produce cosec to the power of n. Cosec to the power, integral of cosec to the power of n. That means they will produce this in. Therefore, the first term would be is equal to in minus 1 into cosec to the power of n minus 2x. Integral of cosec to the power of n minus 2 x would appear, and that integral can be considered as n minus 2. So this total integral can be written as in minus in minus 2. And on the left hand side, we started with this in. So already we have one in on the left hand side, and if we shift this term involving in, its coefficient is equal to n minus 2 with this negative term. So if we shift this in on the left hand side, this negative term would become a positive term, and the coefficient in minus 2 would come along with this in. So if we take this in common, due to this in on the left hand side, one is taken within, is written within bracket, and along with this term n minus 2 would come with this positive sign. So positive of n minus 2 would come. So this would be the left hand side, in into this expression. Whenever it is computed, it would be n minus 1, the total expression, the value of this expression n into n minus 1. And on the right hand side, we have this first term. So this is the first term. Along with that, this negative sign and this negative sign would together produce the positive sign, and we'll have this is n minus 2 multiplied by in minus 2. So we will have n minus 2 in minus 2. Okay, so over here the coefficient of in, that is actually n minus 1. So if we divide the total equation, this total relation, if we divide the total relation by n minus 1, we will have this type of expression. This first term by n minus 1 plus n minus 2 by n minus 1 multiplied by n minus 2. So in this way, we can compute the reduction formula for cosec to the power of n x dx. This is the reduction formula for cosec to the power of n x dx. So similarly, over here I am leaving this one, the reduction formula for sec to the power of n x dx. Hopefully this is all right with you. Now is it clear to you?
Yes, sir.
Clear. And some examples have already discussed over here. You can go through this example. This is the example over here. This is this, in this integral, in this reduction formula. This is the reduction formula for sec to the power of n. This is the reduction formula for sec to the power of n. Now in this reduction formula, with the help of this reduction formula, we can compute the expression of sec to the power of 4x dx, maybe sec to the power of 5 or sec to the power of 6. This kind of expression can be computed. So over here, if you put n is equal to 4 in this integral, in this reduction formula, if you put n is equal to 4, in that case we can compute I2, sorry, I4, and that expression would involve I2. And again, if we put n is equal to 2, we can compute I2. I2 can also be directly computed, because in that case sec square x dx would appear, and sec square x would ultimately, the integral of sec square x is equal to 10x. So you can directly apply that formula as well. So in this fashion, we can compute the integral of sec to the power of 4x dx. Now let me discuss few questions from this exercise, because this kind of questions are generally selected in exam. Hmm. And the question that I am going to discuss is already available in the in this Google Classroom page. Over here under this classwork tab, hmm, I have posted this one under this reduction formula chapter, or this is actually a topic in this Google Classroom. It is called topic. So under this reduction formula topic, already one file, this file reduction formula with some solve problem. This is been posted as a PDF file over here. So if you click on this formula on this PDF file, you will get the corresponding file over here. So you can download it, and whatever I am discussing over here, everything is available in this file. So some standard formula along with some standard solved examples are also available there. So you can go through this file. Okay. So let me discuss the results, because I already have the copy of that file. So let me open that file. Where is the? Oh, I can go through this file as well. No problem. Hmm. So let me solve this question for you. This is a question in your exercise, and this is a very common question in exam. You can go through these questions. I'm discussing this question number 9. It is given that if in is equal to this kind of definite integral from 0 to pi by 2 x to the power of n sine of x dx with n greater than 1, then show that in plus n into n minus 1 in minus 2 is equal to n into pi by 2 to the power of n minus 1. So one important observation that helps us to solve this kind of problem is that in this final expression that we need to prove, you observe that in is there and in minus 2 is there. So that means the index n is reduced by 2. So starting from in, the index is n, it becomes in minus 2. So index becomes n minus 2 after manipulation. After mathematical manipulation, the index becomes n minus 2. So what over here, what is the observation? Observation is that this index of this power of x to the power of n is getting reduced, because this power is associated with this index in. So this x to the power of n we need to integrate this one by parts in such a manner that x to the power of n, the power of x to the power of n has to be reduced. It would be ultimately converted into x to the power of n minus 2. Okay, so that is possible if we consider this expression x to the power of n, if we consider this function x to the power of n as a first function. Got it? If we consider this function of x to the power of n as a first function, then first function is differentiated in the integration by parts, and the second function is integrated. So it is clear that we need to consider this x to the power of n as a first function, and this x sine of x as the second function. So this much is clear from the given question. So if you can have this kind of observation, then that observation would help us to solve the problems. Over here you see x to the power of n sin x dx with the limit 0 to pi by 2, this definite integral is taken as in, where n is greater than 1. And now we are choosing this x to the power of n as the first function, and this sine of x as the second function. So what we need to do, remember these are definite integrals. So in each and every stage you will have to apply the lower and upper limit. So in this first term, we shall have x to the power of n. This is the first function, x to the power of n. And when sine x is integrated, the second function is integrated, we will have negative minus of cos x. Whenever it is integrated, sine x is integrated, we will have minus of cos x. So that would be the first term with lower and upper limit pi by 2, upper limit 0 is the lower limit, minus. Then derivative of first function, that is x to the power of n, its derivative is equal to n into x to the power of n minus 1. Derivative of first function and then integral of second function. So this would be the integral. Now we have one problem. You see over here, we cannot write this expression as equal to in, because in involves sine function and this integral involves cos function. So what can we do? And by the way, I forgot to tell you that if you put x is equal to pi by 2 at the point cos of x, as because cos x is there at the point pi by 2, this cos of pi by 2 becomes is equal to 0. So at the upper limit, the value of this first term would be is equal to 0. And again at the lower limit, this x to the power of n would be equal to 0. So at the lower limit as well, the value of this function is equal to 0. So the contribution coming from this first term would be is equal to 0. Now I was saying that we have we have cos function over here, so we cannot write this integral as this in. So what we need to do, we can again try to make the manipulation so that this cos x is again converted into sine function. So whenever cos x is integrated, it becomes sine function. So what we are applying, we are again applying the integration by parts. Okay, and then this function x to the power of n minus 1, this function is taken as first function and this cos of x has been taken as second function. So what we have, already n should be kept as the factor. And then this x to the power of n minus 1, this is the first function, multiplied by cos of x, the integral of second function. Cos of x should be integrated. Whenever cos of x is integrated, we will have sine of x. So first function is kept fixed, multiplied by integral of second function with the proper upper and lower limit, minus n is already there. So now what we need to do, we need to differentiate the first function. So n minus 1 into x to the power of n minus 2 would come, multiplied by integral of second function. Integral of second function is sine of x dx. So this would be the term. And now if we put lower and upper limit, at the lower x is equal to 0, at the lower limit, this value of this expression would be is equal to 0. So you don't need anything to compute, because at the lower limit is 0, and at the upper limit pi by 2, sine of pi by 2 is equal to 1. So we shall have pi by 2 whole to the power of n minus 1 multiplied by 1 more, multiplied by one more 1. Hmm. So it is the immaterial to multiply by 1. Okay. And then after that n and this n minus 1, these two together would come outside the integral. And now you see, yes, it is now in the given form that x to the power of some expression, some term x to the power of n minus 1. Initially we had x to the power of n. So now we have x to the power of n minus 2, and sine function is there multiplied by the sine of x dx. Got it? So now this integral can be written as in minus 2, as because this function is in, therefore this integral can be written as in minus 2, and therefore this is our in minus 2, and this would be the final expression. You see, this whenever this in minus 2 is taken, is kept on the left hand side, it is taken on the left hand side. It is shifted on the left hand side. So this is the final expression that we had to prove. This was the question, that on the right hand side n into pi by 2 to the power of n minus 1 is there. So in this way we can prove this kind of in this kind of reduction form. And let me discuss one more question from this one, because this has also been selected many a times in exam. It is not a definite integral, it is about indefinite integral. Im comma n is equal to x to the power of m into 1 minus x to the power of n dx. And we have to prove that m plus n im comma n minus 1 is equal to x to the power of m plus 1 multiplied by 1 minus x to the power of n minus 1 plus n minus 1 into im comma n minus 2. This is the next question. This question number 10. So what we observe over here, you see there is a printing mistake, I suppose. Let me check. No. It's okay. No printing mistake is there. Okay. What is our observation over here? You see over here, this n minus 1 is the index on the left hand side, and this index is n minus 2. That means this n is related with the second factor. Got it? So this second factor should be differentiated, because after differentiation the power is reduced. Got it? So we have to consider this we have to consider this function as the first function. We have to consider this function as the first function, because first function is differentiated. Okay, 1 minus x to the power of n, it should be considered as the first function, because the first function is differentiated, and the remaining part x to the power of m should be considered as the second function, because second function is integrated, and after integration x to the power of m would become x to the power of m plus 1. So x to the power of m plus 1 is there, no problem would be there. Got it? So that is the observation we need to have. By looking at the expression, you need to have some observation. And you see, we can continue the process. So this function x to the power of m has to be considered as the second function, and this function 1 minus x to the power of n has to be considered as first function. Got it? So first function is kept constant. We are making the integration by parts. This is the first function, and this is x to the power of m. Whenever it is integrated, we will have x to the power of m plus 1 divided by m plus 1 minus derivative of first function. So n into 1 minus x to the power of n minus 1, and again this 1 minus x has to be differentiated by chain rule. So it would give us minus 1. So this much, this total expression, this much is actually the derivative of first function. This is the first function, 1 minus x to the power of n. So this is the derivative of first function. Okay. And then integral of second function, this x to the power of m should be integrated. So x to the power of m plus 1 divided by m plus 1 dx. Now this n is taken outside the integral. This m plus 1 is taken outside the integral as n by m plus 1. This minus 1 this minus 1 will get adjusted with this minus sign, it will be plus sign. And what we have over here, x to the power of m plus 1 multiplied by 1 minus x to the power of n minus 1. Now what we are doing is that, you see, x to the power of m plus 1, this x to the power of m plus 1 can be written as x to the power of m multiplied by x. Got it? I am telling again, this x to the power of m plus 1 can be written as x to the power of m multiplied by 1 more x, and this x can be written in this way, x minus 1 plus 1. Why? Why are we doing this kind of operation? Because in that case, this integral, you see, this second term, this total expression, this 1 plus x can be multiplied by this 1 minus this x minus 1 can be multiplied by this 1 minus x. Remember, we have x minus 1 and we have 1 minus x. So a negative sign should come over here. That's why this negative sign comes. So what we shall have, x to the power of m multiplied by this factor and this factor. So we will have this n minus 1 multiplied by one more factor, that means 1 minus x to the power of n. Got it? Plus, due to this plus x to the power of m multiplied by this expression. So we will have x to the power of m into 1 minus x to the power of n minus 1 dx. Okay, and this n by n plus 1 is not changed at all, it is kept fixed. Now what we observe over here, you see this term, this integral is actually the given integral. This is the given integral I m comma n. So this integral can be written as I m comma n. We started with I m comma n, and after manipulation we are again getting one more I m comma n. So this term I m comma n should be taken on the left hand side. And what about this integral? You see, x to the power of m is there, and over here 1 minus x to the power of n minus 1 is there, multiplied by dx, of course. So 1 minus x whole to the power of n minus 1 would give us the same kind of integral I m comma n minus 1. In place of n we have n minus 1. Okay, so the second index becomes is equal to n minus 1. Now we are taking we're shifting this term on the left hand side, and we actually already had one more I m comma n, and then we take this I m comma n common, and this is the expression within bracket. And after shifting this term, this is the left hand side, and what is the right hand side? In the right hand side, this term should come over here, so this is the term, and this term should come over here, so this is the term. Got it? And you see over here, if you take the LCM, I am adding one term over here, one extra term over here. Let me add this term. You see, if you take the LCM, this m plus 1 would be is equal to LCM. So 1 this m plus 1 plus n should come. Got it? So this m plus 1, this m plus 1, and this m plus 1, we can cancel all this m plus 1. I'm cancelling this all m plus 1. This m plus 1 and this m plus 1. I'm cancelling all these terms, and therefore we have this term. Got it? That's why I did not write this term, this line. So I'm now removing this, deleting this line. So we ultimately get this kind of expression, and this expression, whenever the total expression is divided by m plus n, we will get the corresponding reduction formula. But there is a difference in that reduction formula. We don't need to divide it, And secondly, in the reduction formula, on the left hand side, we had im comma n minus 1, but we already got im comma n. And on the right hand side, we had im comma n minus 2. If you look at this question, this is im comma n minus 2 on the right hand side, and on the left hand side im comma n minus 1. Actually, we should start from this kind of integral, but by mistake we started with im comma n. So what? No problem. You just replace this n by n minus 1, and in that case, replacing n by n minus 1, you will get this kind of integral im comma n minus 1 multiplied by m plus n, because you see n is replaced by n minus 1. And on the right hand side, we already have x to the power of m plus 1, but this term was 1 minus x to the power of n, and so we have 1 minus x to the power of n minus 1. N is to be replaced by n minus 1. Okay, and this n is to be replaced by n minus 1 over here, and as a result n minus 1 will be replaced by n minus 2. So this gives us the final result that we are supposed to prove. Okay,